All right. Hi, everyone. My name is Markus Ziller. I'm a solutions architect at Amazon Web Services. And today, I want to speak about AWS Lambda, and in particular, how you can optimize your Python applications running on AWS Lambda. Before we get started, can I get a quick show of hands? Who of you is already using AWS Lambda? So 2/3, probably more. All right, for those not using it, I want to start with a brief overview of what AWS Lambda actually is. So, on a very high level, it is a serverless compute service that lets you run code in response to events with pay-as-you-go pricing. So those are the four main components. You don't need to manage servers, you only pay for what you use, and it is event-based. That's important to remember. If we look into this at a bit more detailed level, especially from a customer perspective, for you, what this means is that, well, there's the Lambda service, and what do you do with it? You create functions, and a function is essentially a combination of code you write, in this case Python, but we support many languages, and a configuration of that function. That is the core component of AWS Lambda. And it's not only one function, you can write many functions. What you also do is you manage permissions on that functions. You manage who is allowed to call that function, which service is allowed to call the function, who is allowed to invoke the code in that function. But you also manage what the function is allowed to do. So is the function allowed to interact with other services on AWS? Has it network connectivity? Those are things that you mention. And then at some point, you want to react on an event. And that event can come from a number of different sources. Typical sources is a message queue or an API gateway. And that event comes in from external and then gets mapped to Lambda. And at the end of the day, this is going to be a dict that is passed to your Python function that you wrote. And then you go on and run your business logic. So and if the request comes in, we need to create an execution environment. An execution environment is essentially the place where you run your code. So if you want to run a Lambda function, we need to find a place on one of our servers that the Lambda team owns where your code can run. And then we create an execution environment, and that is part of the lifecycle of a Lambda function. So there are three phases in the lifecycle. One is build and deploy. That is pretty straightforward. For Python, that means running your pip install, just bundling your dependencies, all the code, put it in a zip file, and then upload it, provide it to the service so it can be used by the service. The next stage is the initialization. That is when we create an execution environment, so the place where your code runs. If we don't have an execution environment and someone wants to run your code, we need to, again, find a place on our servers, create the environment, which is a micro VM, download all the code, initialize the code, and then we are ready for the first invocation. And then we are in the handler invocation phase. That is when we actually run the code that you provided to us. Those of you that have already used Lambda might know these phases under different names. So the initialization phase, that is essentially a cold start, because it feels like the Lambda is cold when we need to go and find the place to run your code and create the environment. That adds a bit of latency to the first request. When we have set up the execution environment, that is then a warm start, because the environment is there, either because we pre-provisioned it, or we can reuse it from a previous execution. That's important to remember as well. Then there's another view, that is the pricing view. So there are three components that determine how much you pay for your Lambda function. One is the number of invocations. That is typically per 1 million invocations. Then there is the invocation duration. How long does it take your function from being called to being finished by returning a result or crashing if you're unlucky. And the last part is, what's the size of your Lambda function? So when you create a Lambda function, you define the memory size, and that just determines how much resources we allocate for that function. So the first aspect, that is rather static. That is independent of your workload. This is more 1 million requests cost the same regardless how big your functions are. The other part is dynamic, and we talk about gigabyte seconds here, because we essentially multiply the duration with the gigabyte, and then there's a price tag associated with every gigabyte second. And okay. when we want to write Lambda functions, this looks a bit like this. So this is the Python code. What we see here is a Lambda handler. If you can't read it, it's not super important. It's just an illustration. So it's a Lambda handler. That is the entry point. Whenever the Lambda function is invoked, we call the Lambda handler that you define as, you tell us to run. And this particular example is a Lambda handler for a common scenario, and that is a serverless REST API, where we have some API gateway, we have a Lambda function, so this provides a REST API, this is our backend, and then we have some persistence layer, in this case, NoSQL database called Amazon DynamoDB. And what is then happening is a request comes in, that is retrieved by the API gateway, and it is translated in a dict object that is then passed to your Python function in Lambda. That contains all information about the request, queries, query strings, the body, headers, and so on. We can then take, oh, no, my thing is not working again. We then call the Python handler, and we can process the data. We can extract the user ID, for instance, from the query string, and make a database call, get the data, return the data, and then this is passed back to the API gateway, which converts this back into a response to the API request that we made. So, yeah, number 5. When it comes to building those functions, there are two design philosophies. One is what we call microfunctions, the other is the so-called lambda lift. And those are two ends of a spectrum. You can be in between as well. But essentially, by microfunction, when you have a route, you have one Lambda function per route. Not even per route, but also per HTTP verb. So per every get, for every post. That is what we call a microfunction. And then there's the Lambda lift, where you just have all the requests that come in, get forwarded to the Lambda function. And then logic like authentication and routing, that needs to be handled in your Lambda function. There are some considerations when we reason about this. And when we talk about efficiency, microfunctions have an advantage in the sense that you can easily right-size. You only provision the resources and pay for the resources you need for that particular code execution path. For instance, a GET request might be much more expensive than a POST request. So you can just pick the function size depending on your needs. You can keep the functions lean because you only need the dependencies you require. I know if you use Pillow for image processing, you don't need to have this in every function with a microfunction architecture. Cold starts can happen, but rather infrequently, for infrequently called functions. On the other hand, for the Lambda lift, where you have every logic in one Lambda, the function size impacts the cold start time because it's just more code to download, more things to import, more compute cycles to perform. There's also a 250 megabyte size limit for Lambda functions that you might risk to run into. That is a hard limit. And the function, the Lambda lift, is essentially oversized for all but the most expensive execution path. If you have a very cheap operation, again, you're still going to use the full capacity and going to be built for the full capacity of the function you provided. Security is more fine-grained when it comes to microfunctions, because you can have more fine-grained permissions on what the Lambda can do, but also when it comes to authentication or authorization of your users. And with the Lambda lift, this tends to move more into the code, which is something you might want or might not want. It's not good or bad either. It's just, it depends on your workload. Observability is arguably harder for microfunctions because it requires additional tooling. If you split up this into several Lambda functions, this at the end of the day becomes a distributed system, which is harder to observe. When we talk about automation via infrastructure as code, what we see with microfunctions is that the complexity in your IAC templates is increased compared to the Lambda lift. Because the interdependencies between the different components, you now manage this in your infrastructure as code template. So if you have 10 Lambda functions, that's 10 resources in your CDK, CloudFormation, Terraform, whatever you want to use. While if you have just one function, those complexities move into the code, where the mechanisms to handle those are more established, like think of testing, dependency injection, such things. And lastly, if we talk about operations, you have more granular concurrency controls. So if you have a Lambda function that you want to limit, for instance, for post requests, it's easier to do this in that scenario because you can just use native features of Lambda or API gateway. When it comes to existing applications, Lambda lift is quite easy to lift and shift. If you use frameworks like Flask, there are tools out there that allow you to essentially take your existing code base, throw it to Lambda, and this will work with little work. If you need to split this up, this is work you need to do. So again, there's no right or wrong here. There's an in-between as well. It depends on your workload, but those are the things how we think about those different design approaches. With that being said, I'd now like to talk about optimization techniques that are independent of those design approaches. These are things that you can do for almost every Lambda function, and they have been proven well in practice. Before I go into those techniques, I'd like to preface with what I'm saying with that there's no silver bullet. So at the end of the day, every workload is different. Mine is different, yours is different, and yours is different. So what you need to do is you need to define some metrics where you want to end up. And then you measure and you optimize and you repeat the cycle until you're at the point where you feel comfortable with your workload. It might be if you have a Lambda function that is called a few times a day that you don't need to optimize at all because it is essentially free for all intents and purposes. Nonetheless, let's talk about what you can do. So the first thing I want to do is talk about how you can optimize the Lambda config. So without touching any code, there are a few things that you can do to optimize on the configuration level when you define your Lambda function. And the first thing is the memory setting. So when you create a Lambda function, you set the memory. And Lambda exposes a memory control where you can set the memory from 128 to over 10 GB of memory. And the more memory you set, the more powerful your function becomes. And not only in terms of memory, so RAM, but also in terms of CPU that is allocated to your function and network capacity. And together with the fact about the pricing that we discussed earlier, this leads to an interesting situation where it can actually be cheaper to increase the memory of a Lambda function, thus increasing the cost for that part of the calculation, but reducing the runtime and save cost. Now you can do this manually, but this is a quite tedious process. And I'd like to propose a better alternative, and that is the Lambda power tuning tools. There's an awesome open source framework that allows you to tune your Lambda functions, to right-size your Lambda functions. And what it does is it takes your Lambda function and deploys it in a number of configurations, memory configurations. And then it also takes a payload that is that you typically see in your application, and it invokes all those functions a couple of times, dozens of times, and it tracks those invocations. It tracks the duration, it tracks the configuration, and it tracks the costs that this leads to. And what it then does is at the end, it takes this awesome data, all this data, and creates this awesome visualization. And that allows you to make an informed decision about how your function performs in different scenarios and reason about where you want to set the memory control for your function. So for every non-trivial function, I really encourage you to use this. It is a fantastic way to optimize. There's another aspect to the memory setting, and that is, as I said, it is a proxy for other settings, like CPU, for instance. And there's one magic number that you should remember, that is 1,769. At 1,769, you start to begin to get one CPU, and if you go above that, you proportionally get more vCPUs. So if you have workloads that are I/O bound or CPU bound, it is very likely that you're going to see improvements when you go like this side of the charts. And that is again something that you would be able to find out using the tool I just mentioned. So keep that in mind, play around with the value, we see huge gains. There's a blog post about this, it's a few years old, but it's still relevant, and I think we saw 60–70% performance improvements for multi-threaded workloads. Another thing that I want to mention real quick on the config layer still is Graviton. So I don't know if you knew, but AWS, we build our own CPUs, and they are called Graviton. They are 64-bit ARM cores, and they offer up to 40% better price performance compared to x86 Lambda functions. And it's for interpreted languages like Python, it's almost trivial to set those up to get started with. It's just a change in configuration, and most workloads, 99+%, will just work right away, and you'll save 40%-ish. No promise here. Yeah, that's the config layer, but obviously there's things you can do in the code where you can really optimize your code for performance, for cost, and so on. And what I want to say is the usual best practices still apply. So there's nothing special about running Python on AWS Lambda. It is a runtime for Python codes. All the things you already do because you're awesome and you're a great programmer, continue doing that. And then just treat your handler function like you would treat your main, as a top-level entry point to your code. And then do all the things, keeping the handler minimal, do unit tests, and so on. And that will give you a great baseline for your Lambda function to get started with and maintain clean code, and a thing you can work with easily. There are things that are more specific to Lambda that you can do. A quick win that I recommend to every of my customers is using AWS Lambda typing. There's an open source package that adds type hints to your Lambda functions, to the events that come in, to the responses you can return that are expected by the calling services. And that is very easy to do and saves you a lot of headaches. It makes your life so much easier. So this should be a standard for every Lambda project that you start, for every Python on Lambda project that you start. Another really important thing where we can see huge improvements is execution environment reuse. So to understand what I mean by this is we need to go back to the life cycle. So we have the 3 phases, and where we build and deploy, initialize, and then we call the handler function. And in the handler, we do some things. We might configure some API clients. We might load secrets. We might want to populate a cache or create a database connection. All those things cost compute cycles. And those compute cycles, we will need them for every time the function is invoked. So ideally what we want to do is we want to move this to an earlier stage. We want to have this ideally in the build and deploy stage when we bundle and upload the code, but at latest in the initialization stage. And it looks a bit like this. Code that does this looks a bit like this. So here at the very bottom, that is the handler function. That is the code that is called for every invocation of your Lambda function. The rest, that is only called once. So what we can see here, this runs once, as I said, and then the objects are kept in memory, and they are available for all further invocations within that execution environment. Another advantage of this is that you get up to 10 seconds of boosted host access. So you're not constrained by the limits set via the memory setting, but for up to 10 seconds in the initialization phase, you get boosted access and can utilize more CPU cores and more CPU capacity for your functions. One thing to know or to mention is that code that you run here, that adds to the cold start time, but that is always preferred to the warm start time, because you're going to only see once the cold start time per execution environment. The warm start time, you're going to see that for every invocation, for every execution of your code. And then, yeah, that is run for every handler invocation. So keep this as slim as possible. We recommend to write idempotent code, and idempotency is a bit of a tricky thing, and I can't remember the definition. So the capacity of an application or component to identify repeated events and prevent duplicated, inconsistent, or lost data. At the end of the day, it is about treating duplicated events correctly. And Lambda is an event-driven system, and we have at least one semantics. And there might be cases where you don't care, where you just don't care about duplicated events. But if you are in banking, for instance, and your Lambda function handles financial transactions, you care very much about deduplication, and then at most once semantics, or exactly once semantics. So at the end of the day, this helps you reduce unnecessary API call and prevents data inconsistency. That's the important bit. So if you need this, the easiest way to get started is AWS Lambda Power Tools for Python. That is a framework that we maintain, some utils for Python. I'm going to talk about that later in a second. And what this will do is it will implement this workflow on the left. It will set up a database where that is used to deduplicate your events. And this is annotations based, where you just annotate your handlers and you provide the DynamoDB table, and then you have some function that essentially fingerprints. It creates a token for every event that comes in that you can configure. And then for the first execution, it stores the result in the table. And for any further execution, it looks it up. If it's not there, it runs the execution. Otherwise, it returns the stored result. That guarantees you that this is only executed once. So if you care about idempotent code, best way to do it. Sooner or later, you're going to interact with the rest of AWS, some parts of AWS, if you use Lambda functions. And you're going to use, in most cases, the SDK for Python, which is called Boto3. One thing to know is that it is pre-installed in the execution environment we provisioned for you, but this typically lacks a few minor versions, minor versions behind the most recent version. So as of today, we are 2 minor versions behind, which might not be a big deal, but then at the end of the day, can end up having having different versions in your test environment, in your dev environment, than on the actual Lambda function. Now that's something that you should typically want to avoid, so we recommend you to provide this as part of your bundle. Another thing, if you use other AWS services, you might want to test those. You might want to test the integrations, and for that you can use a great tool called Moto, and that allows you to mock AWS services. Please be aware it's not maintained by AWS. It is a very active community, but it's not an official AWS product. And the way it essentially works is it's a decorator that just mocks out Boto3, the SDK we just talked about. It does not support all API operations. It has a good coverage for the basic operations, S3 put, get, delete. And the recommended use case is fast unit testing, so fast feedback cycles, fast development. But pay attention and do not rely on Moto alone, because it is mature and reliable, but it offers no full coverage, and it is not really suitable to model complex scenarios, complex interdependencies. And it then leads to a false sense of security that can really cause problems. So use this in your dev environment, maybe in a test environment, in your CI/CD pipeline, but always validate against a real environment, with a real Lambda, real DynamoDB, real S3, whatever you want to use. Be mindful about your logs. So we heard about this earlier in the talk by Space Now. Print in the cloud is not free, and it's the same on AWS. So when you print in your Lambda function, this goes to CloudWatch logs, and there's a price point to this, and that is comparatively cheap. It's around 50 cents per gigabyte. And for most Lambda functions, you would not really care about this. You will start to care if your Lambda function has a lot of traffic. So what we see here is the cost of a sample Lambda function, a typical configuration, 512 megabyte of RAM, 1200 milliseconds per request. When you only log around 4 kilobytes, the cost of your CloudWatch logs will exceed the cost of your Lambda function, which is around $500 for 100 requests per second. So avoid logging dynamic data and utilize cost and usage alerts. Set an alarm so whenever you see a spike in CloudWatch log costs to get notified, and some developer forgot the print statement, or configure your linter to highlight those statements. Recursive loops are really dangerous. And that happens when your Lambda function puts data out to some place that causes it to invoke itself again, either directly or most commonly via some message queue. So if you use some Kafka, for instance, and you write into Kafka and then consume from Kafka, then you're going to be in a world of pain. Because a few things are going to happen that are really going to ruin your day. First, it's going to be really expensive. You're going to have high costs for Lambda. You can easily go into the billions of invocations if you just realize what is happening too late, but also for related logs. Imagine the scenario I just gave with CloudWatch logs, where you just log terabytes of data. That's going to be really expensive. Another really unpleasant thing is that it maxes out the Lambda concurrency. So the way Lambda works is there's a concurrency, 3,000 for some, it depends on the region, but 3,000 is the default for some region that can run. And that is how many Lambdas can run in parallel. And that is set on an account level. So if an account with, I don't know, 10 Lambda functions, and one of them goes crazy, it will consume all the capacity, and you're suddenly going to see that your other Lambda functions will not have any capacity left. So the blast radius is as big as your account if that is happening. Plus, there might be other unwanted side effects. Imagine an SNS service that sends out an email for every invocation. You're suddenly blasting your users with tens of thousands of emails, which is not pleasant either. There's an automatic detection built in for SNS and SQS, where we detect recursive loops and prevent those. But this is not the case for every scenario. If you use EventBridge, Kafka, Kinesis, whatever you want to use, you need to keep in mind that you need to be aware that this can happen and mitigate this. So towards the end of my talk, I want to give you 2 recommendations how you can get started with applying what I just said. I mean, this is just talk, but at the end of the day, you need to translate this into your workloads. And the best place to start is serverless land. That is a page that we AWS maintain, which has a lot of resources around serverless. It has patterns, code samples, best practices, workshops, many different things. Also many Python code samples. Python is one of the most used languages for AWS Lambda, and it's a great starting point for everything about serverless. And secondly, the Lambda power tools for Python. I mentioned this in the context of idempotency, but there's much more to it. You can use it for tracing, monitoring, and many other things. It's a really great framework, like 2K stars on GitHub, so it's used quite a lot. And should be more or less a default for every Lambda function you're going to write in Python. All right, that's all I have. If you have questions or anything else, reach out to me, write me an email. Happy to help. Happy to discuss your workload with you, or just find me around. Yeah, thank you.
Thank you, Markus. Will there ever be a way to use MWAA API from Lambda without using AWS CLI? For example, calling MWAA API on S3 upload.
You mean directly in the sense that, because you can do this via, now I get it. Okay, so you don't want to have a Lambda in between the S3 to MWAA path. Is that the question?
Unfortunately, unless the asker is around, I can't really clarify. So the answer is I don't know. There might be. We typically build things when customers ask for it. So if there's enough customer interest, this will come very likely at some point in time. But for now, I don't know. Thank you. Here's a weird question. Do you think the requests pip package is destined to be deprecated and undeprecated every few years?
I don't get the question. The requests package?
The requests package.
Like the Python package?
Yes.
I don't have an opinion on that.
How is power tuning built, since it has to run the function with the different settings repeatedly?
It's a step function. So what step functions is a service where you can provide state machines, and we create a state machine for you where we configure a number of Lambda functions in different configurations, and then the step machine just runs through all the Lambda functions, invokes the function, tracks the results, and then consolidates them.
Thank you. If anybody in the audience has a question, just raise your hand. Is there a plan to add a feature of snap start also to Python lambdas to overcome cold starts?
So what the service team said is they started with Java because the cold start problem was most present there, but they are looking into other languages as well. So I would expect this to come, but I don't know. What I know is that the service team communicated that they're looking into other languages as well.
Thank you. And when should you use batching? How do you decide on the perfect batch configuration for event sources?
So batching is used typically when you use queues or message brokers that are the source of the events that come into your Lambda function. General batching, batch as much as possible. This will make your execution more efficient. There is no generic guidance. I would try to batch as much as possible unless you run into the limits of the Lambda function in terms of maximum duration that it can run or whatever. But in general, batching is a great thing and you should utilize this, especially if we can also use multi-threading on the batch.
That's all the time we have for questions. Thank you, Markus.
All right.